In this series of exercises, you are going to draw the Nyquist plot for certain functions and evaluate the stability of the closed-loop system. Let's start with function L of s equals to 1 over s squared plus s plus 1. The first step here is now to split this function into a real and imaginary part. To do that, we can now replace s with j omega and expand this equation. L of j omega now becomes 1 over j omega squared plus j omega plus 1, which is 1 over 1 minus omega squared plus j omega. J squared is -1. Now we can multiply this by the conjugate of this complex number, so 1 minus omega squared minus j omega, and here also divided by the same 1 minus omega squared times -j omega. Now we can expand this, create two functions, one with the real numerator, the other one with the imaginary part of the numerator. This is 1 minus omega squared divided by 1 minus omega squared squared minus j omega squared plus j times -omega divided by the same 1 minus omega squared minus j omega squared. We can now solve for this. This gives 1 minus omega squared divided by, we don't need to expand that, 1 minus omega squared squared plus omega squared. J squared is -1 times 1 is plus 1 times omega squared plus j times -omega divided by the same. And here we have the real part, clearly shown there. And this is the imaginary part of the function. And this is now what we need to determine the 4 key points in a Nyquist plot. That is, the magnitude and phase when the frequency tends to 0, to infinity, and the real and imaginary axis crossing. So I'm going to write this expression here, and you're going to use this now to find these points on the Nyquist plot. To evaluate the phase and the magnitude of the transfer function, we can place the poles and zeros of this transfer function on the S-plane. This transfer function has 2 poles and no zeros, and you can see that these poles are complex conjugate numbers. The damping ratio is less than 1, so they will be placed on the left side of the S-plane. They have the same real part, and they have conjugate imaginary parts. As if this is aj, this would be -aj. Now we can put in our points of interest. The point of interest that we want to evaluate now is when omega tends to 0. This is the first point on the Nyquist plot. When omega tends to 0, and we are looking again only on the imaginary axis, we are only sweeping now the frequency axis. So omega equals to 0, sigma in frequency domain is always 0, which means that the point we want is here, omega equals to 0. We can now take this point as the reference point and find the angle of all poles and zeros with respect to that point. So here they are. This is one of them. This is another one of them. The angle here is θ1. The angle here would be θ2. Clearly, because these poles are complex conjugate numbers, we can immediately say that θ1 equals to -θ2. They are the same values, but they simply have a different sign. We can now calculate the phase of the entire transfer function when omega tends to 0 as the sum of angle of all zeros. In this case, there is no 0, so that's 0, minus the sum of angles of all poles, which is θ1 plus θ2. Because we know that a θ1 equals to -θ2, this is 0, so the angle of the transfer function is 0. We can now go here to our expression and replace simply omega equals to 0. When omega equals to 0 here, what do we get? We get L of 0 equals to L of 0 gives 1 over 1 plus 0. So the magnitude of L at 0, when frequency is 0, is simply 1. So this is the first point of interest for the Nyquist plot. Let's write it here. When omega tends to 0, we have a phase of 0 and a magnitude of 1. Now we can do the same analysis when the frequency tends to infinity. So I'm going to erase this, and you can repeat the analysis now when the frequency moves towards infinity. Now let's repeat the analysis for a point of interest which corresponds to omega tending to infinity. In this case, our reference point is here and is tending to infinity. Here we have the two poles, same thing we had before. The only difference is that the point now moved from 0 towards infinity. We can now again find the lines that will give us the angles between the poles and the point of interest. Here we have one of them, let's call this theta 1, and here we have another one of them, let's call this one theta 2. Now we know that the frequency tends to infinity. As this point tends to infinity, what are the angles theta 1 and theta 2? Well, clearly they will tend to 90 degrees each. Theta 1 tends to 90 degrees and theta 2 also tends to 90 degrees. Now the phase of the transfer function when the frequency tends to infinity is again the sum of angles of all zeros, which in this case is 0, minus the sum of angles of all poles, 90 degrees for theta 2 and 90 degrees for theta 1. So the phase of our transfer function tends to 180 degrees. Now we can look at the magnitude. What happens to the magnitude when the frequency tends to infinity? We can evaluate L at infinity, and what do we get? We see that the real part will tend to 0 because we have omega squared on top, but we have omega squared to the power of 2. So this is omega to the power of 4. The denominator increases faster than the numerator, the real part goes to 0. Same applies to the imaginary part. You see that we have omega on the numerator and omega to the power of 4 in the denominator. So this term also tends to 0. When omega tends to infinity, the magnitude of the transfer function tends to 0. And the phase tends to negative 180 degrees. I forgot the negative sign here, right? Negative, the sum minus the sum of all poles, 90 plus 90, negative sign, negative 180 degrees. So this is now the second point of interest. This is when omega tends to infinity. And for this case, we found that that the phase is negative 180 degrees, and the magnitude of the function L is 0. We now have two additional points to calculate, the imaginary and the real axis crossing. How do we do that? Well, if we want to find the point where the Nyquist plot crosses the real axis, we simply set the imaginary part to 0. And if you want to find the point where we cross the imaginary axis, then set the real part to 0. So let's do that. To find the real axis crossing, we can now set the imaginary part to 0. The imaginary part is given here. Notice that the imaginary part doesn't include j. J indicates the imaginary part. So now you have negative omega over 1 minus omega squared minus plus omega squared equals to 0. What values of omega will make this tend to 0? Two values. If omega is 0, the numerator is 0, the entire function goes to 0. And if your omega tends to infinity, the denominator is very large, will also make the entire function tend to 0. So the real axis crossing will occur when omega tends to 0 and when omega tends to infinity, which is the same we calculated here. Omega equals to 0 and omega equals to tending to infinity. Where exactly does the Nyquist plot cross the real axis? We can now simply evaluate the function at omega equals to 0 and omega equals to infinity. We already did it. It's here. We'll cross the real axis at 1, at an angle of 0 degrees, of course, and at 0 when the angle is negative 180 degrees. Right. So this analysis gave us exactly what we just found here. So here there is no additional information. Now let's do the imaginary axis crossing. Now in this case, we'll set the real part to 0. And what do we get? If you set the real part to 0, now you have 1 minus omega squared over 1 minus omega squared plus omega squared equals to 0. What values will satisfy this equality? We have 2. If omega equals to 1, the numerator is 0. To solve for that, simply set 1 minus omega squared equals to 0. Omega equals to 1, make this 0, which makes the entire function 0. Or if omega tends to infinity. This will make the denominator very large, much larger than the numerator, and the entire fraction goes to 0. Omega tending to infinity was found here, phase negative 180 degrees and the magnitude of 0. So these are the points where we'll cross the imaginary axis when omega tends to infinity. It will simply tend to 0. What about omega equals to 1? Now, if you want to find the exact point where the Nyquist plot crosses the imaginary axis, we need to evaluate the transfer function at 1 radians per second. If you do this, we have in the first part 0. This is exactly what is solved for here. When omega equals to 1 radians per second, the real part goes to 0. 1 minus 1 is 0. This entire term goes to 0. Plus, here now when omega is 1, we'll find j times negative 1 divided by 0 plus 1, which is simply negative 1. So the magnitude of the transfer function is 1, and the actual value of the transfer function will be plus minus j. This is the point where the Nyquist plot intersects the imaginary axis. So this is now the new point for our analysis. It will cross the imaginary axis at plus minus j. And the real axis crossing occurs at 0 and infinity, which is exactly what we found here. So no additional points are provided through this analysis for drawing the Nyquist plot. We are crossing the real axis exactly where the frequency tends to infinity or to 0. Now that we have all this information, we can finally draw the Nyquist plot. Here we have all points of interest that will help us draw the Nyquist plot. The first one is when the frequency tends to 0. This is our starting point. We have a midpoint where the Nyquist plot crosses the imaginary axis. We have also the information about the crossing of the real axis, which will fall into these 2 here, so no additional points. And you have the final point where the frequency tends to infinity. So let's just start with our starting point, the frequency tending to 0. When the frequency tends to 0, we have a magnitude of 1 and an angle of 0. So we are placed at 1 at an angle of 0. Remember that the angle is the angle of that line that will connect this point to the center of this plane. And in this case, the angle is 0, so we lie on the real axis, on the positive side of the real axis, and the magnitude is 1. So this distance is 1. This is our first point, point 1. The midpoint we found here, the imaginary axis crossing, negative j and plus j. So we are at around here and there. So this is our second point. The third point is the point where the frequency tends to infinity. In that point, when the frequency tends to infinity, now the phase is negative 180 degrees. So we are now lying again on the real axis, but we are on the other side of the imaginary axis. We are now to the left of the imaginary axis. Right? So if this angle here is 0, we go to 1, but now if you go all the way, that is 180 degrees or negative 180 degrees. This indicates that in point 2, we are on the negative side of the real axis. the magnitude tends to 0. So we are lying around here. But notice that we now tend to 0 following a negative 180 degree line. So this Nyquist plot, we have to go to 0 tangent to a line that has a negative 180 degree angle. Now we have all the elements here. This is the second point. This, in fact, is the third point to avoid confusion there. And now we can connect them. We can start from 1. We go to negative j, which is the imaginary axis crossing. And now we have to tend to 0 following a negative 180 degree line. So the only solution is that the Nyquist plot will do this. Notice how it tends to 0, and it does so following a negative 180 degree angle. This is half of the Nyquist plot, but we know that the Nyquist plot is always symmetric with respect to the real axis, which means that the complete Nyquist plot should look like this. We know that the Nyquist plot goes clockwise. We went from this point to that point, so this will also go clockwise like that. Now we can evaluate the stability of our system. We are concerned with encirclements of -1. Now that we have the Nyquist plot, we can finally evaluate the stability of the closed loop system. We are now concerned with encirclements of -1. What can we conclude about the stability of this system? Clearly, this system is always stable. It does not encircle -1. Even if you multiply this function by a very large gain, all what that does is it will expand the size of the Nyquist plot, but because now the Nyquist plot tends to 0 following this 180 degree, I will never encircle -1. So this system is always stable.